So let me make some comments. So suppose we have the group SON, where n is an even number, say 2k. Then what is the rank of the group? Can someone tell me? Okay, I think it's time for a break. So I'm going to leave you here and maybe someone can tell me after the break. Okay. So we'll meet back here at 6:15. Okay.
Could you scroll up a little bit?
Yeah. So I'll leave it here. Okay. So we'll meet back here at 6:15. Well, let's say 6:20 because it's already 6:05. So we'll meet back here at 6:20. Okay, so let's start again. So did anyone come up with an answer for this question? Okay, let me give you a way to think about it. Okay, so, when we're considering, say, rotations in, say, 2k dimensions, we know that we can pair up the dimensions and those planes, if we pair them up, as long as none of the directions coincide between the different planes, those will be independent rotations, right? So if we are in 2k, then if I say, well, I'm going to rotate in 1, 2, and 3, 4, and 5, 6, ... 2k minus 1 and 2k, then these are independent rotations, right? So those rotations will all commute. So does that tells us that all the the matrices, all the generators which correspond to those rotations will be mutually commuting. So the number of generators in the Cartan subalgebra is how much? What is the dimension? How many generators are here? Okay, this index goes to 2k, and we are pairing up. We are having 2 in each. Exactly. So the dimension of the Cartan subalgebra is k. Okay, so for SO2k, now if I am considering, say, rotations in 2k plus 1, this extra dimension is, can I pair it up with any other direction? Right, so suppose I'm in three, I'm in 3 dimensions. I have 1, 2, that's one rotation, and that's it. The third direction cannot be paired up with any other direction, right? So, so this is the case for SO3. For SO2, we only have two directions. So here we have only the Cartan subalgebra is one-dimensional. What would be the Cartan subalgebra for this case?
Also one?
Exactly. So the rank of SO5, so the rank of SO5 and the rank of SO4, they're both the same. Okay. And then when we go to SO6, the rank jumps to 3. And when we go to SO7, it's 3. Because this extra direction doesn't have a pair to give you another independent rotation, right? So do you see the intuition behind the Cartan subalgebra? The counting of the dimension of the Cartan subalgebra?
Yes, sir.
Okay, very good. All right, so that's the rank. So I'm going to move on to a generalization of the ON groups. But before doing that, do we have any questions? Okay, so we are going to generalize to the orthogonal group to the O, N, comma, N. So, previously we saw that the Lorentz group in 2 dimensions was given by O1, comma 1, right? And in the tutorial, you were supposed to show that the Lorentz group in 3 + 1 dimensional space-time is O1, comma 3. So how are these groups defined? It's a set of matrices. We usually use lambda for that, such that lambda transpose eta, lambda is equals to eta, right? Where eta is a rank 2 tensor, which can be written as a matrix. And for the case of O1, comma 3, it's given by -1 + 1 + 1 + 1. Right? So this is basically, now, what is the dimension of this of this group? So again, we have to count the number of independent components and the number of constraints, right? So the number of independent components here, the number of real entries is 16, right? This matrix has 16 entries. But this equation, if I write it explicitly, it's going to be mu nu eta, sorry, let me use a different index here. Mu rho eta mu nu lambda nu sigma eta rho sigma. And this is symmetric. So the counting here is exactly the same as the counting of ON. So here we will have the same number of constraints as before. So in this case, the number of constraints would be 10. And therefore, given that we have 16 independent, 16 entries in a O1, 3 matrix, means that the dimension would be 6, right? That would be the dimension of SO1, 3. Okay. So it is clear that why this equation, the equation before was O I K O Kj is equals to delta Ij. Here this was symmetric in Ij, here it's symmetric in rho and sigma. You know, so the left-hand side is also symmetric, right? But here, instead of eta, we had a delta. Okay, any questions?
Sir, is SO13 the Lorentz group in 4 dimensions?
Yeah, exactly.
Okay.
This is the Lorentz group that's relevant for us. Okay.
Okay.
The other one was like a toy Lorentz group. So similarly, we can define O n comma m to be the set of matrices. So O n comma m would be the set of matrices such that this equation is preserved, where eta mu nu has basically n time-like direction and m space-like directions, okay? This is just a mathematical curiosity, or we don't usually use groups like this because why? Because we only have one tangent directions, right? I mean, this is a fact of nature. Okay. So this is just a generalization, okay? And the dimension would be, if you define big N to be N plus M, then the dimension would be N minus 1 by 2. Okay, so let me make some comments. And comment number 1 is what Fiza was saying. SO1, 3, which is a subgroup of O1, 3, is the group of continuous Lorentz transformations and so these are the transformations which are continuously connected to the identity, right? So now if we just consider the rotations, then that's a subgroup of SO1, 3, right? So the rotations would be SO3, it's a subgroup of SO1, 3. So all the matrices of SO1, 3, where the time component is 1, and so these are the matrices which form SO1, 3. Sorry, SO3, right? Now, if you consider the boosts in Lorentz transformations, there's actually a further restriction on SO1, 3. So the physical Lorentz transformations that we use require, okay, the physical Lorentz transformations such as say, rotations and the boosts require a further restriction and that is that the 0,0 component of the Lorentz transformation matrix must be positive. Okay, because if I look at the Lorentz transformation matrix, it's a 4x4 matrix, and this component is 0, lambda 0, 0, and that must be positive. Why? This ensures that the light cone structure is preserved. I'm going to unpack this statement. Light cone structure is preserved. That means that, remember that in special relativity, space-time is given for every point, every event, we have a light cone structure. We have something called, so if this is an event, then all the time-like vectors in the future light cone, all these points are called future, right? And all these points are called past. And this is neither past, neither future. This is elsewhere. And future pointing vectors are of this form, and past pointing vectors are of this form. These are 4 vectors. And the Lorentz transformations, which have lambda 0, 0 positive, ensure that the transformation does not transform a future pointing vector to a past pointing vector, and vice versa. It preserves the causal structure. Okay. So lambda 0, 0 being positive ensures that a Lorentz transformation does not transform a future pointing interval or vector into a past pointing one. Into a past pointing one. And vice versa. Okay, so this part of the Lorentz transformation, so SO1, 3 with lambda 0, 0 greater than 0 is called the proper. The proper relates to the fact that it has S equals to 1, the proper orthochronous Lorentz group. Okay, so it's a subgroup of SO1, 3, and it's denoted by SO1, 3 plus. Okay. So this is the Lorentz group that we mostly use in physics, at least in classical physics. Okay, are there any questions at this point?